Find dy over dx if x cubed plus y cubed equals 1. We could actually go through and get y as a function of x here, but I want to use implicit differentiation here because I think it's going to be a little bit easier. But we can look at this one both ways, actually. I think that's a good idea. So let's first use implicit differentiation. So we need to differentiate both sides with respect to x. So the derivative with respect to x of x cubed plus y cubed equals the derivative with respect to x of 1. All right, so let's differentiate the left-hand side. The derivative of x cubed is 3x squared, plus, we've got to use the chain rule here because y is a function of x. So the derivative of y cubed is 3y squared, but then we've got to multiply by y prime, the derivative of the inside. Now on the right, the derivative of 1 is 0, so that is easy and good to go. Now, if we want to solve for y prime, we've got to subtract 3x squared from both sides. So it's going to give us 3y squared y prime equals negative 3x squared. And then to get the y prime alone, we need to get rid of that 3y squared. So we're going to divide both sides by 3y squared. Those 3's on the right are going to cancel, and we're going to have negative x squared over y squared. So that is the derivative. We also could write this equation in the form where y is a function of x. If we have x cubed plus y cubed equals 1, we could subtract x cubed from both sides, giving us y cubed equals 1 minus x cubed. And then we can take the cube root of both sides to get y alone. That gives us y equals the cube root of 1 minus x cubed. Or we could think of this as y equals 1 minus x cubed to the 1/3 power, either way. And remember, we don't have any problems with taking the cube root of both sides like we did with the square root. Because with the square root, there's the positive square root and the negative square root. But with cube roots, that doesn't actually happen. We don't have an issue. The cube root function is a 1-to-1 function. So we can cube root both sides of that. And then we can use the power rule and the chain rule to differentiate this. So we've got y prime equals, well, the derivative of u to the 1/3 power is 1/3 times u to the negative 2/3 power, right? When we use the power rule, we subtract 1 from the exponent, and 1/3 minus 1 is negative 2/3. And then we have to multiply by the derivative of the inside, because this is a composition of functions. The derivative of the inside is just going to be negative 3x squared, right? Because the derivative of 1 is 0, and then we've got minus the derivative of x cubed. That's going to be negative 3x squared. Now, let's see what happens. We can see that the 3's are going to cancel. We've got a 3 in the denominator and a 3 up top. And so we've got this negative x squared. I'm actually going to put that in the top. And then in the bottom, we've got 1 minus x cubed to the 2/3 power. Remember that negative exponent tells us to move it into the denominator. And so this is what we get when we don't use implicit differentiation. Now, these two things look different, but they are in fact equivalent because remember, we have 1 minus x cubed over here, and that's the same as y cubed. 1 minus x cubed is equal to y cubed. So we could replace these parentheses with y cubed, and y cubed to the 2/3 power is the same as y squared, which is exactly what we have over here. So these two things are equivalent to each other. I think that it's a little bit easier to use implicit differentiation. This was less work than what we did over here. But the benefit to doing it this way is that we have everything in terms of x. So the derivative is a proper function of x. instead of written in terms of x and y. So there are pros and cons to both methods in a situation where we could choose either method. But remember, sometimes we can't solve for y in terms of x, and we're required to use implicit differentiation. So it's really good to get good practice so that you're capable of using that whenever you need to.